This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Week 3, Lesson 10, the Refrigeration Capstone. No new theory. You already own the vapor compression cycle and its pH diagram, superheat and subcooling, compressor work and displacement, multi-stage and absorption, the per-ton comparison, line sizing, and cold storage loads. This lesson is the method under exam pressure. Name the machine, route each quantity to the right printed equation or table, and solve. We'll work 4 problems: a cycle's COP and tonnage from 4 chart enthalpies, the compressor work and displacement per ton, a single effect absorption COP, and a 3-stage cold storage load. Then lock in the week's traps. The decision map. Every refrigeration problem is one of a few shapes, so name the machine first. A vapor compression cycle gives you COP, capacity, and compressor work from 4 enthalpies read off the pH chart. An absorption machine gives you an ideal COP from 4 temperatures. A load problem sums sensible and latent from the food property table. And the per-ton comparison table already lists refrigerating effect, displacement, power, and COP side by side. The cycle formulas live in Chapter 4. The property and comparison data live in Chapter 8. Identify the shape, reach for the pill, solve. Problem 1. The vapor compression cycle. Read the 4 state enthalpies off the pH chart. The refrigerating effect is 1 minus 4, 64 BTU per pound. The compressor work is 2 minus 1, 12. COP of refrigeration is 64 over 12, about 5.3. The heat absorbed is mass flow times refrigerating effect, 38,400 BTU per hour, and dividing by 12,000 gives 3.2 tons. Notice the heat pump COP is exactly 1 more than the refrigeration COP. Same compressor, and heat rejected equals heat absorbed plus the work. Problem 2. Same cycle, now the compressor. Work is mass flow times the enthalpy rise, 120 BTU per minute, or 7,200 an hour, about 2.8 horsepower. Displacement is the actual volume the compressor swallows. Mass flow times the suction-specific volume, 6.6 cubic feet per minute. Divide by the 3.2 tons, and you get just over 2 cubic feet per minute per ton. The key is the suction-specific volume. The compressor breathes low-pressure vapor, not liquid, and the per-ton table lists that displacement column for you directly. Problem 3. A single-effect absorption chiller. Everything here is absolute temperature, so convert to Rankine first. Generator 660, rejection 560, evaporator 500. The ideal COP is the generator factor times the evaporator factor times the condenser over absorber factor. Because the absorber and condenser reject to the same loop, that last factor is 1, and the ideal COP works out to about 1.26. Then check the generator clears its minimum firing temperature, 160 Fahrenheit. 200 is fine. But remember, 1.26 is a ceiling. The rule of thumb lands near 0.9, and a real single-effect machine delivers COP around 0.7 to 0.8. Problem 4. A cold storage load. Freezing beef from 50 degrees to 0. Build it in 3 stages. Sensible above freezing. Mass times the above freezing specific heat times the 22-degree drop to the freezing point. 33,900 BTU. Latent effusion. Mass times the heat of fusion. 164,000. The biggest piece by far. Sensible below freezing. Mass times the lower below freezing specific heat times the last 28 degrees. 30,800. Sum is about 229,000 BTU. Over a 10-hour pull-down, that's roughly 1.9 tons. Freezing is most of the load, and you must switch to the below freezing specific heat for the last stage. The week's traps in one screen. On the cycle and compressor, the refrigeration ton is 12,000 BTU per hour, not the 15,000 cooling tower ton. The heat pump COP is exactly 1 more than the refrigeration COP. Throttling is isenthalpic, so stakes 3 and 4 share an enthalpy. Displacement rides on the suction-specific volume, and you read the enthalpies off the chart yourself. On absorption, food, and units, every absorption COP uses absolute temperatures, and the 4-temperature form is a ceiling, not the field value. Switch to the below freezing specific heat once you cross the freezing point. A product load is sensible plus latent plus sensible, and if a method isn't printed, the problem gives you the number. Look up discipline. The cycle math lives in Chapter 4, Section 4.5, the vapor compression cycle, the COP definitions and the ton, the compressor work, and the two-stage cycle. Everything else lives in Chapter 8, the absorption COP, the per-ton comparison, the property charts and saturation tables for R22 and R134A, the refrigerant safety classes, the line sizing tables, and the food-specific heats. Know which chapter owns the quantity, jump to the section, read the row, and confirm. Never search from scratch under the clock. The method and the clock. Before you compute, name the machine, vapor compression, absorption, or a load problem, because that alone picks your formula set. For a vapor compression cycle, read the 4 enthalpies, then COP, capacity, tons, and work. For absorption, put the 4 temperatures in Rankine, take the ideal COP, and confirm the generator clears its minimum. For a cold storage load, sum the 3 stages and divide by the pull-down hours. Keep the units the formulas expect, enthalpy in BTU per pound, every COP ratio in absolute temperature. And if a method isn't printed, the problem gives you the number. That's a wrap on Week 3, Refrigeration, 10 lessons, with the cycle core in Chapter 4 and the application data in Chapter 8. The vapor compression cycle and pH diagram, superheat and subcooling, compressor work and displacement, multi-stage and cascade systems, absorption, refrigerants, and safety, the per-ton comparison, line sizing, and food and cold storage loads. Then this capstone, tying them together under time. More HVAC weeks are on the way. Subscribe so the next one reaches you. Everything's at PEPrepengine.com. A cheat sheet, worked solutions, and a short quiz are attached here. If the course helped, please subscribe, and good luck on exam day.
The full study guide with every equation and common exam trap is free at PEPrepengine.com, link in the description. Structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.